Welcome back to the Deep Dive, where we plunge headfirst into the technologies not just shaping our future, but actively colliding to create it. Today, the future isn't just coming, it's here. And it's, well, frankly, mind-bending. We're talking about two colossal technological shifts, artificial intelligence and quantum computing. They're no longer separate entities on parallel tracks. They're merging to birth something truly transformative. And this isn't merely about building faster computers. It's a fundamental reimagining of what computation itself can achieve, really pushing the boundaries of what we thought possible. Our mission today is to take a deep dive into this incredible fusion, quantum AI. We're going to unpack what happens when the logic-defying principles of quantum mechanics meet the powerful, pervasive learning capabilities of artificial intelligence. We'll explore its profound implications for everything from our digital security and the global financial world to the cars we drive and, yeah, even the very fabric of our ethical considerations. Our goal, as always, is to provide you with a shortcut to being truly well-informed, armed with some surprising facts, and maybe just enough humor to keep you utterly hooked. Prepare for some delightful brain stretching.
Yeah, it's really tempting to relegate this kind of discussion to the realm of science fiction, isn't it? Something out of a futuristic blockbuster, maybe. But the reality, as we'll uncover today, is that the advent of quantum AI presents both an unprecedented opportunity and a transformative, immediate challenge to contemporary systems. We're talking about technologies that underpin our daily lives, from the encryption algorithms that, secure your online banking and shopping, to how governments and industries worldwide manage their most sensitive data. The stakes are, quite frankly, extraordinarily high, and it's happening much faster than many people realize.
Okay, let's unpack this fascinating collision then. The term quantum AI might sound like something dreamt up by a particularly imaginative sci-fi writer, but it's very much a present-day scientific endeavor, isn't it? It seems like it's rapidly moving from the theoretical to the tangible. So to kick us off, what exactly is quantum AI, and what makes this combination so profoundly groundbreaking that it warrants our attention right now?
Right. So at its core, quantum AI, or QAI, is the powerful, almost inevitable convergence of quantum computing and artificial intelligence. What's crucial to understand is that we're not just talking about making our current computers a bit smaller or incrementally faster, or even just optimizing existing AI algorithms. This isn't just an upgrade, you see. It represents a fundamental revolutionary shift in how we process information, how we understand learning, and how we approach problem solving at a really foundational level.
Okay, so a whole new paradigm, not just faster versions of what we have.
Exactly. Artificial intelligence, as we know it today, has already revolutionized countless industries, right? It helps analyze colossal data sets, identify intricate patterns, make highly informed decisions across sectors from healthcare to logistics. We see it everywhere. But quantum computing, with its unique magical properties, has the potential to elevate these capabilities to an entirely new level, an almost unimaginable level.
How so? What's the key difference in processing?
Instead of processing data one binary bit at a time, a 0 or a 1, quantum computers leverage qubits. And these qubits can process incredibly complex information, exploring vast numbers of possibilities simultaneously at speeds that classical machines simply cannot touch.
Right, that simultaneous processing is key. And you mentioned it's important to distinguish QAI from something else, quantum machine learning, QML.
Yes, that's a really important distinction. While QML is a vital part of this broader landscape, focusing on, for instance, developing machine learning algorithms that run on quantum computers, or maybe creating quantum versions of classical machine learning models, QAI aims for something even more disruptive, maybe more existential, you could say.
More disruptive how? What kind of concepts are we talking about?
It envisions a future where the very foundations of intelligence and computation are built on quantum principles. Imagine concepts like truly intelligent systems that could understand and generate natural language with a nuance beyond anything we've seen today. Or sophisticated sentiment analysis performed with an understanding of human emotions so deep it almost borders on empathy, all within a quantum environment.
Wow. So it's about fundamentally rethinking what intelligence itself means when you infuse it with quantum power.
Precisely. It's about pushing past the boundaries of what classical computing can ever really hope to achieve. And for those listening, you might be thinking, okay, this sounds fascinating, but why now? Why is this sudden, complex convergence so urgent for me to understand?
Yeah, what's the immediate relevance?
The real insight here is that the quantum clock isn't just ticking for some theoretical future threat. It's actually revealing a fundamental flaw in the security architecture we've relied on for decades. It demands a radical, immediate rethink, not just a minor upgrade down the
A
line.
flaw. What
Yeah.
flaw exactly?
The urgency primarily stems from the transformative challenge that quantum computing poses to our current cybersecurity landscape. Right now, the vast majority of our digital lives, your online banking, your private messages, national security secrets, intellectual property, they're secured by widely used encryption algorithms. Things like RSA, ECC, Diffie-Hellman.
The standard stuff we rely on every day without thinking about it.
Exactly. And these systems rely on mathematical problems that are currently hard for classical computers to solve in any reasonable time frame. Factoring large numbers, for instance. The looming specter of quantum computing, specifically algorithms like Shor's, which we'll get into, has the potential to render these algorithms utterly vulnerable. It could transform them from these impenetrable digital fortresses into mere sandcastles.
So effectively, if a sufficiently powerful quantum computer comes online, and many predict it's a question of when, not if, then much of our current digital security could simply crumble, exposing a staggering amount of sensitive information.
That's the stark reality, yes. It's not a scare tactic. It's a cryptographic reality we need to prepare for proactively.
Okay, that sounds concerning. But surely it's not all doom and gloom. There must be opportunities, too.
Oh, absolutely not all doom and gloom. Quite the opposite in many ways. For forward-thinking investors, for instance, understanding these developments isn't just about risk mitigation. It's absolutely crucial for navigating the evolving financial landscape and identifying potential growth areas.
So spotting the next big thing, basically.
In a sense, yes. This isn't just about future-proofing your security. It's about recognizing a technological revolution that isn't just on the horizon anymore. It's practically at our doorstep. It demands our attention and proactive engagement. This is about seizing monumental opportunities in a rapidly evolving world.
Okay, here's where it gets really interesting and, frankly, a bit mind-bending, as you said. To truly grasp the revolutionary nature of quantum AI, we first need to get a handle on the quantum part. So take a deep breath, everyone, because we're about to delve into some physics that will likely redefine your understanding of how computation works. Expert, we're all familiar with classical computers, or laptops and smartphones, operating on simple bits. Can you walk us through what a qubit actually is? What makes it so fundamentally different and powerful?
Absolutely. The fundamental difference lies right there in their basic unit of information. As you said, classical computers operate on bits. A bit is a binary choice. It can be either a 0 or a 1. Think of it like a simple light switch. It's either definitively on or definitively off, a clear, unambiguous state. Now, enter the quantum realm and everything gets delightfully weirder.
Delightfully weirder. I like that. Okay, bring on the weirdness.
Quantum computers introduce something called a qubit, a quantum bit. And here's where the magic, or maybe the quantum weirdness, begins. A qubit can be a 0, a 1, or both at the same time.
Wait, hold on. Both at the same time? How does that even work? My brain just did a little flip there.
It's thanks to a core quantum phenomenon called superposition. Imagine that classic light switch isn't just on or off, but it can also be in a state of being partially on and partially off simultaneously. Or maybe think of it as spinning, embodying all potential states at once until you actually look at it, until you measure it.
Okay, spinning light switch.
Or another way to visualize it, instead of just existing as a point on an X or Y axis, a qubit can be anywhere on the surface of a sphere, often called the Bloch sphere. This represents an infinite number of possible combinations of 0 and 1 simultaneously.
Infinite possibilities on a sphere.
Okay. This vastly expands its ability to store and process information. While a classical bit holds just one value, a qubit holds a whole spectrum of probabilities for both 0 and 1. This incredible richness gives it computational power far, far beyond classical bits.
And how do you get it into that state? That both at one state?
To get qubits into this state of superposition, we often use what's called a Hadamard gate. It's essentially a specific quantum operation, like a tiny instruction, that places a qubit into an equal superposition of 0 and 1.
Okay, a Hadamard gate puts it in a superposition. That sphere analogy helps. It's like being able to hold multiple versions of reality in its head at once. What other quantum superpowers does a qubit possess? Superposition is already pretty wild.
Beyond superposition, there's entanglement, which is frankly even more mind-bending. This is where quantum mechanics truly departs from our everyday classical physics intuition.
Even more mind-bending. Okay, I'm ready.
Entanglement creates an instantaneous, unbreakable link between two or more qubits. Changes made to one qubit instantly affect the others, regardless of the physical distance separating them. Miles apart, light years apart, doesn't matter. The connection is instant.
Instantaneous. Faster than light.
It appears that way, yes. Erwin Schrödinger famously called this phenomenon spooky action at a distance, because it seemed to defy the classical understanding of locality that things can only influence their immediate surroundings.
Spooky action. I can see why. So it's like having two coins, maybe miles apart, but if you flip one and it lands on heads, the other one instantly lands on heads too, every single time,
Yeah,
without any signal passing between them.
exactly. It's not just a correlation like they happen to land the same way sometimes. It's an intrinsic fundamental connection where their fates are perfectly intertwined.
Wow. So my analogy earlier, superposition is like reading every book in a library at once. Entanglement would be like having two of those books, no matter how far apart, always opening to the exact same page if you open one.
That's a pretty good analogy, yes. It captures that instantaneous locked connection.
And how do you achieve this spooky connection? What's the quantum gate for that?
We achieve this profound connection between qubits using another specific quantum logic gate known as a CNOT gate, or controlled NOT gate. It's a fundamental operation in quantum computing that essentially entangles two qubits based on the state of one of them.
Okay, CNOT for entanglement. So superposition and entanglement. These are the keys.
These are quantum superpowers, yes. They are what enable truly parallel processing. While classical computing performs tasks serially, one step after another, quantum computing can leverage superposition and entanglement to explore multiple computational paths simultaneously.
So instead of one calculation at a time, it's doing potentially millions or billions at once.
Exactly. This represents a massive, potentially exponential leap in processing power for certain types of problems. It allows quantum computers to tackle calculations that are completely intractable for even the most powerful classical supercomputers today.
That's a huge difference from our everyday computers. But I imagine, as you hinted, such delicate operations must require a very specific, very stable environment, right? You can't just run a quantum computer on your desk next to your coffee mug.
You absolutely cannot. And this is where the really significant engineering challenges become apparent. This immense power comes with significant environmental demands. Unlike your laptop, which happily runs at room temperature.
Sometimes too happily, gets quite warm.
Indeed. Quantum computers require an incredibly stable and, crucially, an extremely cold environment. They often operate at temperatures chillingly close to absolute 0 Kelvin, specifically around 10 millikelvin.
10 millikelvin. How cold is that in real terms?
It's significantly colder than deep space, colder than pretty much anywhere in the natural universe.
Wow, okay. Why so cold?
This frigid condition is absolutely necessary to prevent something called decoherence. Decoherence is essentially when qubits lose their delicate quantum state, their superposition or entanglement, due to interactions with their environment.
What kind of interaction?
Even the slightest noise, a tiny vibration, a stray electromagnetic field, or even minute power fluctuations can cause them to decohere or fall out of their quantum state. This leads to computational errors, making the results unreliable.
So the cold basically keeps them quiet and stable, quantumly speaking.
Exactly. Maintaining such an extreme, isolated environment is a testament to the incredible engineering required to make quantum computing a reality. And it's one of the major reasons why these machines are currently so large, complex, and expensive. #3. The algorithms that keep cryptographers up at night. Now, these unique properties of quantum mechanics, superposition, entanglement, they aren't just for theoretical physicists doing abstract thought experiments in a super cold lab. They've led to the development of specific algorithms that could, quite literally, break the internet as we know it. They could expose our most secure data.
Okay, this is where the rubber truly meets the road for our current digital security, isn't it? This is why the urgency we talked about earlier is so palpable.
Precise.
And the undisputed heavyweight champion in this realm, the algorithm that apparently gives cryptographers nightmares, is Shor's algorithm, developed back in the 1990s by mathematician Peter Shor. This algorithm sounds like a game changer, potentially breaking virtually all existing public key crypto systems.
That's exactly right. It's pivotal. Why is it such a threat? Because it efficiently solves two specific mathematical problems that underpin almost all of our current digital security infrastructure.
Which problems are those?
First, the integer factorization problem. This is the basis for widely used encryption like RSA and the digital signature algorithm, basically finding the prime factors of a very large number. Second, the discrete logarithm problem for finite fields, which is used in key exchange protocols like Diffie-Hellman.
And these problems are hard for normal computers.
Extremely hard. To give you a real sense of the scale of this threat, current encryption, which, by the way, quietly secures about 90% of our data today, everything from your WhatsApp messages to the financial transactions of global banks, relies on these very problems being hard for classical computers. Hard means it would take them an impossibly long time to solve. For a large number used in RSA, factoring it into its prime components would take even the most powerful classical supercomputers available today, potentially billions of years. It's computationally unfeasible.
Billions of years. Okay, that sounds pretty secure.
It is secure against classical computers, but Shor's algorithm, running on a sufficiently powerful quantum computer, could potentially collapse that time frame. Instead of billions of years, it might take just minutes, or maybe even seconds, depending on the scale of the quantum computer.
Minutes, seconds, or billions of years. That's not just faster, that's a fundamental break.
It's a difference so profound, it's like comparing walking across an entire continent to teleporting instantly. It forces us to completely redefine what secure even means in a cryptographic context. Because the mathematical hard problems our entire digital trust is built upon, well, they turn out to be fundamentally easy while viewed through a quantum lens, thanks to Shor.
That is genuinely unsettling from a security standpoint. Okay, so Shor's is the big one for breaking encryption. But I hear there's another famous quantum algorithm, Grover's. What does that one do? How does it compare?
Indeed, then there's Grover's algorithm, introduced by Grover in 1996. While Shor's algorithm aims to break asymmetric encryption by finding those mathematical keys, the factors or logarithms, Grover's is more like a super search engine. This quantum algorithm provides a significant speedup, specifically a quadratic speedup for unstructured search problems.
Unstructured search.
Yeah.
Like finding a needle in a haystack.
Exactly like that. Think about searching for a specific name in a massive unsorted phone book, or a specific data item in a huge database without any index. A classical algorithm, on average, might have to check roughly half of the items in the list. In computational terms, we say that takes about O(n) time, where n is the total number of items. If you have a list of 1 million items, you might, on average, check 500,000.
Okay, that makes sense. Check till you find it.
Grover's algorithm, however, can find the desired item much faster. It takes approximately O(n) time, square root of n.
Square root, so for that million item list, instead of 500,000 checks.
It would take roughly the square root of 1 million, which is only about 1,000 steps.
1,000 instead of 500,000. That's still a massive improvement. Not quite the teleportation speedup of Shor's against its specific problems, but still incredibly significant.
It is a very significant acceleration, yes. A quadratic speedup is powerful.
How does it achieve this without just checking everything faster? What's the quantum trick?
It achieves this remarkable feat by leveraging those quantum properties we discussed, superposition and interference, through a series of carefully orchestrated iterative steps. We call these Grover iterations. Each iteration involves 2 key quantum operations. First, there's an oracle operation. This subtly marks or flags the target state you're looking for, often by shifting its phase, making it quantumly distinct. Second, there's a diffusion transformation, sometimes called inversion about the mean. This operation essentially amplifies the probability amplitude of that marked state while simultaneously diminishing the amplitudes of all the other unmarked states.
So it sort of boosts the signal of the right answer and cancels out the noise of the wrong ones.
That's a good way to think about it, yes. Through repeated iterations, this process subtly but powerfully increases the probability that when you finally measure the qubits, you'll get the target item you were searching for.
Okay, so Grover's is a super searcher. What's its impact on security compared to Shor's?
While Grover's is incredibly powerful for specific search tasks, including potentially speeding up brute force attacks against symmetric key encryption, like AES, its impact is generally considered less critical and more mitigatable than Shor's direct existential threat to asymmetric public key encryption. Because Grover's only provides a quadratic speedup, you can often counteract its effect simply by doubling the key length for symmetric algorithms. For example, moving from AES 128 to AES 256 makes a Grover's-based attack vastly harder again. Shor's algorithm, on the other hand, provides an exponential speed-up against the core problems of RSA and ECC. Doubling the key length barely slows it down. It requires entirely new types of algorithms.
Got it. So Shor's breaks the foundation of public key crypto, while Grover's makes searching faster, which has implications but can be countered more easily for symmetric keys. Grover's is like a very efficient detective, maybe, whereas Shor's is the master safecracker who makes the safe itself obsolete.
That's an excellent analogy, yes.
Okay, we've just painted a picture of quantum's incredible power, both its potential to empower us and its potential to disrupt, especially our security. But here's where the story takes a truly fascinating turn, isn't it? This isn't just a tale of one revolutionary technology threatening another. It seems to be about a deeply intertwined future where AI and quantum computing don't just coexist, but actively elevate each other. They achieve things together that neither could ever accomplish alone. So, expert, let's explore this powerful and mutually beneficial partnership. How can artificial intelligence actually help quantum computing overcome some of its inherent, well, quantum challenges, those fragility issues we discussed?
That's a fantastic way to put it, a powerful synergy, a symbiosis. Let's start exactly there. How AI can actually help quantum computing overcome some of its biggest practical hurdles. Remember those incredibly fragile qubits we talked about? One of the absolute biggest challenges for quantum hardware right now is noise reduction and preventing decoherence.
Right, the tendency for them to lose their quantum state due to environmental interference.
Exactly. Qubits are exquisitely sensitive. Any environmental disturbance, the slightest vibration, a stray electromagnetic field, tiny power fluctuations can cause them to lose their delicate quantum state, falling out of superposition or entanglement. This is a major source of errors in current quantum systems. It makes them difficult to scale up reliably and difficult to sustain complex calculations on.
So how can AI help with that?
AI, with its unparalleled ability to detect incredibly subtle and complex patterns within noisy, complex data, could be absolutely crucial here. Imagine using AI to constantly monitor the quantum system's environment, identifying the precise sources of this disruptive noise in real time. AI could potentially predict when and why decoherence is likely to occur based on subtle precursors. And even better, it could help develop real-time active feedback mechanisms to reduce that noise or compensate for its effects, helping qubits maintain their quantum integrity for longer, allowing for more complex and reliable calculations.
That's fascinating. So AI could essentially act as a sophisticated quantum whisperer, constantly fine-tuning the environment and correcting for disturbances to keep the qubits stable.
Precisely. A quantum whisperer, or perhaps a very diligent quantum caretaker.
And another crucial area where AI can lend a hand, especially given the cryptographic threats we just discussed with Shor's algorithm, is in creating quantum-safe algorithms, right? Defending against the threat.
Exactly. As we've highlighted, Shor's algorithm poses that direct existential threat to our current public key encryption. The task of designing entirely new cryptographic algorithms that are inherently resistant to these quantum attacks, what we call post-quantum cryptography or PQC, is incredibly complex. It requires navigating intricate mathematical landscapes, often based on problems like lattice-based cryptography or code-based cryptography that are still being actively explored and understood.
It sounds like a huge mathematical challenge.
It is. And AI can assist significantly in this delicate balancing act. AI can help researchers design potential PQC algorithms, optimize their parameters for both security and efficiency, and even help validate their resilience against known classical and potential quantum attacks. Think of AI as an incredibly intelligent co-designer, or perhaps a tireless cryptanalyst, helping us forge the next generation of secure communication in this cryptographic arms race.
So AI can help make quantum computers more robust by reducing noise and help create defenses against the threats those quantum computers pose. It's wonderfully ironic, isn't it?
It really is a fascinating interplay.
And you mentioned earlier the sort of holy grail of quantum computing achieving quantum advantage. Can AI help accelerate that journey too, getting to the point where quantum computers are genuinely superior for certain tasks?
Absolutely. AI can play a critical role in accelerating the journey toward achieving quantum advantage. Quantum advantage, just to recap, is that crucial point where a quantum computer can provably perform a specific calculation or solve a particular problem demonstrably faster or more efficiently than any conceivable classical computer, no matter how powerful.
We're not quite there yet for many complex, real-world problems, right?
Not broadly, no, although there are specific tailored demonstrations. But AI can help us get there faster. How? By simulating quantum systems on classical hardware. Even our best supercomputers can't fully simulate large quantum computers, but AI techniques can help us model and approximate the behavior of smaller quantum systems or specific quantum algorithms much more efficiently than traditional simulation methods.
So we can test ideas without needing the full quantum hardware yet.
Exactly. This allows researchers to model potential quantum algorithms, optimize hardware designs, and figure out how to best utilize quantum properties like superposition and entanglement for specific computational tasks before we have large-scale, fault-tolerant quantum computers widely available. This AI-powered simulation and optimization helps accelerate the discovery and refinement cycle for both quantum algorithms and hardware designs, ultimately propelling us closer to achieving that elusive, broad quantum advantage across more domains.
Okay, that makes perfect sense. AI helps build better quantum computers and defenses. Now, let's flip the script. We've seen how AI bolsters quantum computing, but how can quantum computing, with its mind-bending capabilities, help AI reach potentially unprecedented levels of intelligence and efficiency? How can it help AI solve problems that classical AI just, well, can't?
This is where the potential gets truly exciting for the future of artificial intelligence itself. One of the perennial challenges in AI development today, something data scientists spend a huge amount of time on, is enhanced data cleansing.
Garbage in, garbage out, right? The quality of the training data is paramount.
Precisely. AI models are, quite literally, only as good as the data they're trained on. Many organizations grapple with absolutely massive data sets that are often messy, incomplete, inconsistent, or full of noise and errors. The process of cleaning, organizing, structuring, and preparing this data for AI training is incredibly time-consuming and resource-intensive using classical computers. It often consumes a huge percentage of the overall effort in any AI project.
I've heard data scientists say it's 80% of the work sometimes.
That figure is often quoted, yes. Now, quantum computing, with its inherent ability to process vast data sets more efficiently and crucially, to identify very subtle patterns, correlations, and anomalies that classical methods might completely miss, can lead to significantly cleaner, more optimized, and potentially more insightful data being fed into AI models.
So better quality data, faster.
Potentially, yes. And cleaner, better represented data, in turn, results in a vastly improved, more accurate, more robust, and potentially less biased AI learning process. Imagine the precision and the novel insights an AI could glean if it was trained on truly pristine, perfectly represented data.
That certainly sounds like a game changer for AI performance.
Yeah.
But beyond just cleaner data, what's the most profound shift this quantum power could enable in how AI actually learns and evolves? What kinds of problems can quantum-enhanced AI solve that classical AI simply throws its hands up at?
That's an excellent question, and it brings us to the realm of computationally hard problems, specifically a class known as NP-hard problems.
NP-hard. Sounds
Yeah.
intimidating. What are they?
These are extremely complex mathematical problems where finding an exact optimal solution becomes exponentially harder as the problem size increases. For even moderately sized NP-hard problems, finding the perfect solution using classical computers could take an astronomically long time, think centuries, millennia, or even longer than the age of the universe.
Longer than the age of the universe. Seriously. What kind of problems are these?
We're talking about things like optimizing the logistics for incredibly complex global supply chains with thousands of variables and constraints, or perfectly scheduling highly interdependent operations across vast networks like airline routes or manufacturing processes, discovering new life-saving drugs by accurately simulating the quantum interactions of complex molecules. That's inherently a quantum problem. Or performing deep, exhaustive analysis of vast amounts of complex computer code to identify subtle security vulnerabilities or potential optimizations.
Okay, these sound like incredibly valuable problems to solve.
Hugely valuable. Classical AI and optimization algorithms can often find good approximate solutions for these, or they might take an unacceptably long time to find the exact optimum. Quantum AI, leveraging algorithms like quantum annealing or variational quantum eigensolvers, holds the promise of being able to tackle some of these NP-hard problems and find optimal or near-optimal solutions in minutes or even seconds.
Minutes or seconds for problems that take classical computers eons.
That's the potential, yes. It would revolutionize entire fields and unlock solutions that were previously mathematically impossible within human timescales. It's like having a computational cheat code for some of the universe's toughest optimization and simulation puzzles.
That's truly mind-boggling potential. And I understand this convergence also leads us beyond just accelerating classical AI tasks towards entirely new architectures like quantum neural networks. How are they different?
Absolutely. Quantum neural networks, or QNNs, are not just about taking existing classical neural networks and running them faster on quantum hardware. They represent a fundamental reimagining of how artificial neural networks themselves can operate. By leveraging quantum principles again, superposition and entanglement, maybe quantum interference directly within the network structure and processing. These QNNs have the potential to accelerate core AI operations like complex matrix multiplications, tensor decompositions, and the training process of deep learning algorithms in novel ways.
Faster training is always good.
Faster training, yes, which could allow AI models to learn from much larger datasets or develop more intricate internal representations much more quickly. But potentially more significantly, QNNs might be able to capture complex correlations and patterns in data that are simply inaccessible to classical neural networks due to their classical limitations. This could lead to the development of far more robust, nuanced, and potentially more powerful and efficient AI models than what we can achieve today. It's like upgrading the very engine of AI itself, moving perhaps from a classical engine to a quantum-powered one. And importantly, this isn't just theoretical anymore, sitting purely in research papers. Quantum AI, this blend of quantum computing and AI techniques, is already showing incredible promise and starting to make tangible waves across numerous industries. It's truly fascinating to see where these two powerful technologies are converging right now and creating real-world impact, or at least clear pathways to impact, not in some distant sci-fi future.
Okay, let's dive into those applications. Let's start with one of the most critical areas for all of us, augmenting cybersecurity. Given the threats quantum poses, it's reassuring to hear it can also be part of the solution. How does this fusion make our online lives safer?
It really promises to revolutionize how we protect our digital world, offering a multi-pronged defense. Firstly, imagine quantum-enhanced AI for threat detection. Quantum machine learning, or QML, running on quantum hardware or simulated quantum approaches, might be able to uncover incredibly subtle patterns and correlations in network traffic or user behavior patterns indicative of a cyber attack that are simply impossible for classical AI systems to detect in real time due to the sheer volume and complexity of the data.
Finding the needle in the haystack again. But this time the needle is a sophisticated hacker.
Exactly. This could include identifying highly sophisticated, stealthy attacks or spotting minute anomalies that might signal a novel, zero-day vulnerability being exploited, those brand new attacks that currently often catch us off guard. The potential processing power allows for a much deeper, more nuanced, and more instantaneous analysis of security data streams.
So it's like having a security system that doesn't just check against a list of known threats, but can actually detect entirely new unknown forms of attack as they happen, or even slightly before they fully materialize. That's a whole new level of proactive defense.
That's the goal, yes. A truly predictive and adaptive defense. Beyond just detection, think about AI-driven quantum cryptography management. As we transition to those post-quantum cryptographic algorithms we discussed, managing this shift across vast, complex, interconnected global systems will be incredibly challenging.
Just replacing all the locks, essentially.
A massive digital rekeying, yes. AI will be crucial in managing this complex process, optimizing the distribution of new quantum-safe keys, managing cryptographic inventories, knowing what crypto is used where, ensuring seamless integration without breaking things, and perhaps even dynamically adapting cryptographic protocols based on perceived threat levels. It enables better, easier, and more robust data encryption management during this critical transition.
So AI helps manage the PQC rollout. What else in cyber?
Furthermore, quantum AI for advanced risk analysis. QAI could supercharge AI's existing ability to perform deep risk assessments on complex systems. It could potentially identify obscure, interconnected vulnerabilities, perhaps a combination of several minor weaknesses that together create a major hole that classical analysis might miss. This allows for proactive patching and prevention before attackers can exploit them. The sheer speed and complexity of analysis QAI could offer would be transformative for cyber defense, moving us from a reactive posture to a genuinely predictive and preventative one.
Okay, that sounds hugely promising for security. Now, moving from protecting our data to protecting our money, let's look at financial services. This is a sector constantly looking for any tiny algorithmic edge. How will quantum AI revolutionize this high-stakes world?
Oh, it's poised to fundamentally transform it. Several key areas stand out. Quantum computing could revolutionize financial modeling. Think about optimizing incredibly complex trading strategies in real time, sifting through vast streams of global market data with unprecedented speed to identify fleeting arbitrage opportunities or predict market movements with higher accuracy.
Finding those micro opportunities faster than anyone else.
Exactly. It could also significantly improve fraud detection by finding minute, highly complex anomalies in transaction patterns across millions of accounts. Anomalies that might indicate sophisticated fraud rings but look like noise to classical AI. It will accelerate complex financial simulations for risk management, allowing banks and investment firms to model potential market crashes, assess portfolio risk under extreme scenarios, or calculate complex regulatory metrics like value at risk, ValueR, with far greater precision and speed.
So better understanding and managing risk.
And it could price complex financial derivatives, options, swaps, etc., far more efficiently and accurately than current classical methods allow. This leads to more accurate valuations, tighter bid-ask spreads, and potentially more efficient liquid markets overall. We're talking about a leap in analytical power that could fundamentally reshape market dynamics and give an unparalleled edge to those firms that successfully embrace it.
And this convergence, this quantum AI synergy, it doesn't just create new things, it also supercharges AI's already expansive role in finance, right?
Right.
What existing AI applications will get a quantum boost?
Absolutely. You'll likely see significant enhancements across the board. Everything from delivering hyper-personalized, truly tailored banking products based on a much deeper real-time understanding of your precise financial habits and goals, to more intelligent and genuinely helpful chatbots that can handle complex, nuanced customer queries far beyond the basic FAQs they manage today, maybe even showing a degree of simulated empathy.
Better customer service, potentially.
Potentially. It will almost certainly lead to far more accurate credit scoring models, incorporating many more subtle variables, more sophisticated sentiment analysis that can gauge market mood or predict consumer behavior by analyzing vast amounts of text, news, and social media data in real time with deeper understanding, and more robust robo-advisors that can manage investment portfolios with greater nuance, dynamically adjusting strategies based on complex market signals. Areas like high-frequency algorithmic trading and even back-office functions like claims processing and insurance will all become significantly more efficient, precise, and predictive.
So for investors listening, understanding these shifts isn't just academic.
Not at all. It's key to identifying not just the emerging risks from disruption, but also the monumental growth opportunities within this rapidly evolving financial technology, or fintech, landscape. It's about where the smart money will flow next.
Okay, moving beyond finance, let's think about autonomous vehicles. This is a field where real-time, ultra-fast, and highly accurate decision-making is literally a matter of life and death. How does QAI drive us closer to truly intelligent, safe, self-driving cars?
It has incredible potential here, primarily through enhanced perception and decision-making. QAI could potentially process the torrent of sensor data coming from a self-driving car, LiDAR, radar, cameras, ultrasound, GPS, B2X communication, much better and faster than classical systems.
Integrating all that data seamlessly.
Yes, integrating it to build a far more complete, accurate, and nuanced picture of the car's environment in real time. This allows the autonomous vehicle to perceive its surroundings with greater fidelity, understanding not just what objects are there, but predicting their likely behavior, understanding complex traffic interactions. This, in turn, enables the car to make critical, split-second decisions navigating complex, unpredictable environments like busy city intersections, sudden obstacles appearing, or treacherous weather conditions with a level of intelligence and reliability that might approach or even exceed human capabilities.
So moving from just reacting to truly understanding and anticipating.
That's the goal. Researchers are already actively testing specific QAI approaches, like quantum reinforcement learning, for complex driving tasks, such as executing perfectly smooth and safe lane change maneuvers under various dense traffic conditions. It's about teaching the car nuanced skills.
So it's about making the car not just aware, but truly understanding its environment in a way that maybe classical AI struggles to fully achieve with current limitations. And what's truly exciting, I read, is how QAI can improve the vehicles themselves, beyond just the driving software.
Indeed. This is another fascinating avenue. QAI has the profound potential to accelerate the discovery and design of new, more sustainable materials, particularly for things like batteries.
Better batteries are key for EVs.
Absolutely critical. Imagine using quantum simulations, powered by QAI, to design a new battery chemistry, a material that holds significantly more charge per kilogram, charges much faster, lasts longer, and crucially, uses far less rare earth elements like cobalt or lithium, or maybe none at all. QAI can rapidly simulate the quantum mechanical properties of millions or billions of potential material combinations, identifying promising candidates far faster than traditional trial and error lab work.
So faster material discovery.
Much faster. This could lead to breakthroughs that make electric and autonomous vehicles dramatically more efficient, affordable, longer range, and importantly, more environmentally friendly by reducing reliance on precious, finite resources and decreasing overall energy consumption. It addresses critical challenges in sustainable transportation and energy independence.
And that potential impact extends even further, doesn't it? To sustainable energy itself, beyond just transport. What kind of breakthroughs could QAI unlock there?
Yes, while still primarily in the lab for now, QAI holds immense promise here too. It could accelerate the discovery of new, more efficient materials for energy storage, not just batteries, but perhaps other forms like hydrogen storage materials.
Oh.
Also, for next-generation solar panels, finding materials that convert sunlight to electricity with much higher efficiency, or catalysts for cleaner industrial processes or carbon capture technologies.
How does it speed things up compared to how we do material science now?
Classical material science is often a slow, painstaking, iterative process of synthesis, testing, analysis, repeat. QAI, with its ability to accurately simulate molecular interactions and complex quantum phenomena at a fundamental level, can rapidly screen billions of potential material structures and compositions computationally. It can predict their properties before they are even synthesized in the lab, identifying the most promising candidates for achieving, say, super efficiency in solar cells or revolutionary energy storage capacity. Imagine a future where we unlock breakthroughs in clean energy generation and storage much faster than ever before, dramatically accelerating our transition to a greener, more sustainable planet.
That's a hugely inspiring prospect.
Yeah.
And finally, for the increasingly connected world of the Internet of Things, or IoT, and real-time decision-making, QAI seems to offer a solution to a growing data deluge problem. Traditional AI often gets overwhelmed by the sheer volume and velocity of real-time data streaming from countless connected devices, doesn't it?
It absolutely does. Processing and making sense of that relentless flood of data from sensors and smart cities, factories, supply chains, wearables. It's a massive computational challenge for classical systems, leading to delays or suboptimal decisions. QAI, however, with its potential for massive parallelism and optimization capabilities, could theoretically manage this complexity with remarkable ease. It could enable truly instantaneous, globally optimized decision-making across vast interconnected networks.
Can you give an example?
Sure. Volkswagen, for instance, has been exploring quantum computing, potentially coupled with AI, to manage complex urban traffic flow in real time. Using data from potentially thousands or millions of IoT sensors embedded in infrastructure and vehicles, QAI could optimize traffic light timings, suggest optimal routes for individual vehicles, and dynamically manage congestion for entire cities, far more effectively than current systems.
Smoothing out traffic jams for everyone simultaneously.
That's the idea. Similarly, in advanced manufacturing industry, 4.0 QAI could analyze subtle sensor data from thousands of machines on a factory floor to predict potential breakdowns before they happen, identifying faint vibrational anomalies or temperature shifts that signal impending failure. This enables proactive, predictive maintenance, preventing costly downtime and optimizing production schedules.
So moving from simply collecting data to truly understanding and optimizing every interconnected process in real time.
Exactly. These applications are still largely experimental or in early pilot stages, but the promise for profound real-world optimization across countless domains, logistics, energy grids, environmental monitoring, healthcare is clear and incredibly compelling.
Okay, so the potential applications are staggering. But as with any truly revolutionary technology, especially one as powerful and potentially transformative as quantum AI, the path forward isn't perfectly smooth, is it? There are significant technical hurdles still to overcome, and maybe even more importantly, profound ethical considerations that we, as a society, need to grapple with, probably starting right now before this technology truly goes mainstream. It really feels like a double-edged sword, full of both immense promise and potential peril.
Absolutely. That's a very accurate assessment. Let's start with the very real, very tangible technical hurdles for the quantum hardware itself. We're talking about fundamental engineering challenges that are pushing the absolute boundaries of physics and material science. Firstly, as we touched on, there's the issue of instability and errors. Remember how delicate those qubits are?
A decoherence problem.
Exactly. They're incredibly sensitive to environmental disturbances, noise, vibrations, temperature fluctuations. This makes them prone to errors, losing their quantum state during a calculation. Building fault-tolerant quantum computer systems that can detect and correct these errors automatically is a monumental challenge that requires potentially millions of physical qubit to encode just one robust logical qubit. We're not there yet at scale.
So reliability is still a major issue. What else?
Secondly, scalability is a huge ongoing challenge. Current quantum computers, while impressive proofs of concept, are generally limited to performing relatively small tasks with, tens or maybe a few hundred noisy qubits. Achieving systems with thousands or millions of high-quality interconnected and controllable qubits, the scale required for truly groundbreaking, fault-tolerant applications like breaking current encryption or revolutionizing drug discovery, that's going to require significant breakthroughs in qubit design, fabrication, control, and interconnection. It's a massive engineering lift.
Going from dozens to millions is a big leap.
A very big leap. And thirdly, there are those infamous cryogenic demands we discussed. Unlike classical computers that operate comfortably at room temperature, most leading quantum computing modalities require those extremely cold temperatures, often near absolute 0 Kelvin, around 10 millikelvin, using complex dilution refrigerators.
The giant super-cold fridges.
Essentially, yes. This need for complex, expensive, energy-intensive, and specialized cooling infrastructure significantly impacts the practicality, cost, and accessibility of widespread adoption, especially outside large research labs or major corporations.
So it's not just about building better qubits, it's building this entire incredibly complex, cold, quiet ecosystem to protect and control them. And it's not just the hardware side that's challenging, is it? The software, the actual quantum algorithms themselves, also pose their own unique difficulties.
You're spot on. Algorithm development for quantum AI is a beast of its own. It's incredibly difficult to design algorithms that truly unlock the full exponential power of quantum computing.
Why is it so hard?
Because quantum mechanics operates according to rules that are fundamentally different, often counterintuitive, compared to classical physics and classical computation. We can't just take our existing classical algorithms and easily adapt them to run on a quantum computer and expect a magical speed-up. It doesn't work like that for most problems. We often have to invent entirely new ways of thinking computationally, designing algorithms from the ground up, specifically leveraging quantum phenomena like superposition, entanglement, and interference. This requires a deep and often non-intuitive understanding of quantum principles.
It sounds like it requires a whole new kind of programmer or computer scientist.
It does, to some extent. It's a rare and highly specialized skill set currently. And the inherent complexity of designing and verifying these novel quantum algorithms means progress in developing truly useful, game-changing applications can be slower than the incredibly rapid advancements we often see in the classical AI world.
Okay, so technical hurdles in hardware and software. Now let's turn to the perhaps even trickier part, the ethics. It's clear that this technology presents incredible power, and with that power comes significant responsibility. What are some of the key ethical concerns magnified by quantum AI that we really need to be talking about proactively right now?
That's a crucial point, perhaps the most crucial in the long run, and it's where we need to be most vigilant as this technology develops. One major concern, carrying over from classical AI but potentially amplified, is bias.
AI bias is already a huge issue. How does quantum potentially make it worse?
Just like classical AI, if quantum AI models are trained on historical data that contains existing human biases data that isn't reflective of all genders, races, socioeconomic situations, age groups, abilities, geographical locations, etc., then the resulting QAI system will likely learn and perpetuate those biases. And given the potential power and opacity of QAI, it might even amplify those biases in subtle or unforeseen ways, making biased outcomes even more entrenched and harder to detect or correct.
Where is this most critical?
This is critically important, absolutely vital, in sensitive application areas like criminal justice, predictive policing, sentencing recommendations, healthcare, diagnostic tools, treatment plans, hiring algorithms, or financial lending decisions. Biased QAI in these domains could have devastating, discriminatory, real-world consequences for individuals and communities. We need to be designing fairness metrics, auditing processes, and robust human oversight mechanisms right from the outset, not as an afterthought.
So bias is a major risk. Beyond bias, what about the potential for misuse, given the sheer computational power we're discussing?
Yes, there's certainly the very real and concerning potential for weaponization. The prospect of using advanced AI, potentially supercharged by quantum computing, in warfare raises deeply alarming questions. Think about fully autonomous weapon systems capable of making life or death decisions without human intervention, enhanced global surveillance capabilities far beyond what's possible today, or the potential for quantum computers to break adversaries' encryption during conflict. We urgently need robust international dialogue, treaties, and clear ethical guidelines to prevent an uncontrolled arms race in AI and quantum capabilities.
That's a sobering thought. What about understanding these systems? AI is often called a black box. Does quantum make that worse?
It potentially could, yes. This is the transparency and explainability problem. Even with classical AI, especially complex deep learning models, we often struggle to understand precisely how the AI arrived at a specific decision or prediction. It operates like a black box. When you combine this inherent complexity of AI with the fundamentally non-intuitive probabilistic nature of quantum mechanics, understanding the underlying logic or reasoning process of a quantum AI system could become even more opaque and challenging.
Why does that matter so much?
Understanding why a system makes a decision is absolutely crucial for building trust, ensuring accountability when things go wrong, debugging errors, verifying fairness, and preventing unintended harmful consequences, especially in critical applications like medicine or autonomous driving. We need significant research into explainable QAI.
Okay, bias, weaponization, transparency, and thinking about the sheer scale of these potential operations, especially the cooling for quantum computers. Is there an environmental impact we should consider?
Absolutely. That's another important ethical dimension. The energy required for cooling current quantum computers down to near absolute zero using those large dilution refrigerators is substantial. Combine that with the significant and growing energy footprint required to train and run large, complex classical AI models, and the potential combined energy consumption of scaled-up quantum AI in the future could become a significant environmental concern, if not addressed proactively.
So we need green quantum computing too.
Essentially, yes. Research is urgently needed to develop more energy-efficient quantum computing hardware, perhaps operating at higher temperatures, and also more energy-efficient classical and quantum algorithms from the ground up. We need to ensure the development of QAI is environmentally sustainable.
And just generally, with any powerful new tech, there are always unforeseen consequences, right?
History teaches us that lesson repeatedly. Emerging technologies, think of the printing press, the internal combustion engine, the internet, social media, always bring unexpected societal outcomes, both positive and negative, that few, if any, predicted at their inception. Quantum AI, potentially the most powerful technology we've ever conceived, will undoubtedly be no different. The overarching societal concerns around security, individual privacy, mass surveillance, job displacement, and the concentration of power and control will only be magnified in this new era. We need proactive foresight, scenario planning, and adaptable governance structures to navigate these uncharted waters.
Which brings us perfectly to that delicate balance you mentioned earlier, regulation versus innovation. How do we possibly navigate that tightrope successfully with something moving this fast and with such high stakes?
That is indeed the trillion-dollar question, isn't it? It's incredibly difficult. We absolutely need thoughtful regulation and robust governance frameworks around these emerging technologies because of their profound societal importance and inherent risks. We can't just let it be a Wild West, but at the same time, we need to be extremely careful not to stifle the rapid innovation and potentially enormous benefits with overly restrictive, premature, or poorly designed rules that don't understand the technology.
Like happened with early internet regulation attempts, maybe.
Or, as some experts suggest, perhaps early, ill-fitting blockchain regulations in certain jurisdictions might have inadvertently slowed down its initial development or pushed innovation elsewhere. Striking that perfect adaptive balance, fostering rapid innovation while simultaneously ensuring safety, ethics, accountability, and equitable distribution of benefits will be absolutely critical for QAI's responsible development and deployment globally. It requires a nuanced, ongoing collaborative dialogue and approach involving governments, industry leaders, researchers, ethicists, and the public. #7 Solutions and the Quantum Safe Future. But despite all those daunting challenges we've just discussed, from the incredibly fragile qubits and the complex algorithms to those deep ethical minefields, the global community is definitely not standing still. Far from it. Active, innovative solutions are being developed at an incredible pace, particularly on the cybersecurity front. The transition to a quantum-safe cybersecurity landscape isn't merely an option or something to think about later, it's increasingly seen as an urgent imperative. A non-negotiable step to protect our digital future and ensure the continued stability of our interconnected world.
That's reassuring to hear. And the most prominent solution being actively developed right now, the main line of defense being built, is post-quantum cryptography, or PQC. Can you break down what this involves?
Certainly. PQC is an entire field of cryptography dedicated specifically to designing, analyzing, and standardizing cryptographic algorithms that can remain secure even when attacked by the full capabilities of a large-scale, fault-tolerant quantum computer, particularly the threat posed by Shor's algorithm to public key systems. It's essentially a global, collaborative race against time, but it's a race that's fostering incredible innovation in areas of mathematics and computer science that were perhaps neglected before.
And there's a formal process for choosing these new algorithms.
Yes, a critically important and urgent effort in this race is the NIST standardization process. NIST, the National Institute of Standards and Technology in the U.S., has been running a multi-year open international competition to evaluate and select the most promising quantum-resistant public key cryptographic algorithms. This involves incredibly rigorous testing, public scrutiny, detailed cryptanalysis by experts worldwide, and performance benchmarking to ensure that the chosen algorithms are truly secure against both classical and quantum attacks, efficient enough for practical use, and ready for global adoption across the internet and beyond. Several winners and candidates have already been announced.
Okay, so NIST is leading the charge on standardization. You mentioned it's not just one magic bullet, but a diversified portfolio of cryptographic defenses being considered. What are these main mathematical approaches that PQC relies on?
Exactly. Diversity is key for resilience. There are several main families of mathematical problems being used. First, and perhaps the most prominent finalist in the NIST process, we have lattice-based cryptography.
Lattices, like a grid.
Think of it like an incredibly complex, high-dimensional grid or mesh of points in space. Lattice-based cryptography builds its security on mathematical problems related to finding specific hidden points or short vectors within these vast, intricate, multidimensional structures. These problems are currently believed to be very hard, even for quantum computers, to solve efficiently. Lattice-based methods are considered remarkably robust against Shor's algorithm. They tend to be relatively efficient for many operations, and some schemes offer reasonably small key sizes compared to other PQC approaches, making them leading candidates for widespread post-quantum security.
Okay, complex high-dimensional grids.
Yeah.
Hard to navigate even for quantum computers. That makes intuitive sense. What's the next main approach?
Then there's code-based cryptography. This family relies on the inherent difficulty of decoding general linear error-correcting codes, especially when they've been intentionally disguised or had errors added. It's like trying to reconstruct a message that's been deliberately garbled according to a complex, secret rulebook. Code-based methods are generally quite efficient for encryption and have a long history, with some schemes dating back decades. They have a distinct mathematical structure from lattice-based methods, offering valuable diversity. The classic McAleese crypto system is a well-known example that's also part of the NIST process.
So, based on error correction codes, got it, and the final primary candidate family.
Finally, we have multivariate cryptography. This approach uses systems of quadratic or higher-degree polynomial equations over finite fields, essentially, solving complex systems of equations. It often aims for very compact digital signatures or keys, which can be a significant advantage for practical deployment in resource-constrained environments like smart cards or IoT devices. However, multivariate schemes have also historically faced some specific types of algebraic attacks, so their design requires careful management to ensure long-term security. So, as you can see, each approach lattices, codes, multivariate equations, and there are others, like hash-based signatures too, has its unique mathematical underpinnings, its own strengths, weaknesses, performance characteristics, and security assumptions. Researchers and NIST are carefully weighing all these factors to build a truly robust, multi-layered defense for the quantum era.
That makes sense. Don't put all your eggs in one mathematical basket. Now, beyond these purely mathematical algorithm solutions, I've also heard about something quite different called quantum key distribution, or QKD. How does that fit into the picture? Is it competing with PQC?
QKD is a fascinating and fundamentally different approach. It's generally seen as complementary to PQC rather than directly competing because it addresses a different part of the security problem specifically, the secure distribution of secret keys, rather than the encryption algorithms themselves. QKD leverages the fundamental principles of quantum physics itself, like the uncertainty principle or properties of entangled photons, to generate and distribute encryption keys between two parties.
How does quantum physics make the key distribution secure?
The beauty of QKD lies in its inherent security guarantee based on physics, not just mathematical assumptions of difficulty. Any attempt by an eavesdropper, often called Eve, to intercept or even just measure the quantum state of the photons carrying the key information inevitably disturbs that delicate quantum state in a detectable way.
So you know immediately if someone is listening in.
Exactly. The laws of quantum mechanics themselves ensure that any eavesdropping attempt leaves an unavoidable trace, alerting the legitimate users, Alice and Bob, that the key has been compromised, so they can discard it and try again. It offers a physical, rather than purely mathematical, guarantee against eavesdropping on the key exchange itself.
Has this been used in the real world?
Yes, it has. For instance, Vienna established the world's first citywide QKD network way back in 2007, providing ultra-secure communication channels for municipal governments and financial institutions over dedicated fiber optic links. There are growing deployments elsewhere, too, often for high-security government or enterprise needs. It demonstrates its practical viability for highly secure, typically point-to-point communication links.
Okay, so PQC protects the encryption itself. QKD protects the key sharing. Now, implementing all this sounds like a monumental task. It's not just about creating these new systems. It's also about integrating them seamlessly with our vast existing internet infrastructure, right? How do we manage that transition?
It is indeed a monumental task, arguably one of the biggest cryptographic transitions the internet have ever faced. And it requires a proactive, carefully planned, globally coordinated effort. A clear roadmap for seamlessly integrating quantum-resistant cryptography, PQC, into our existing internet infrastructure is absolutely essential. This involves upgrading critical components across the entire internet stack.
Like what specifically?
Things like upgrading the security of the domain name system, DNS, using PQC-based signatures, DNS-SEC. Transitioning secure web traffic protocols like TLS-SSL to versions that incorporate quantum-resistant key exchange and authentication, sometimes called quantum TLS or QTLS. It also involves developing and deploying intermediate hybrid transition protocols where systems might use both a classical algorithm and a PQC algorithm simultaneously for a period, ensuring security even if one proves vulnerable later.
Hedging your bets during the transition.
Exactly. The ultimate goal is to migrate the entire ecosystem, servers, browsers, routers, applications, embedded devices to these new, more secure PQC standards, while crucially retaining user trust, ensuring interoperability, and avoiding the accidental introduction of new vulnerabilities or major disruptions during this complex, likely multi-year transition period. It's a massive digital renovation project for the entire planet.
Wow, okay. And what about blockchain technology? It relies heavily on cryptography. Isn't it vulnerable too?
Right.
Are there quantum-safe blockchain solutions?
That's another critical area, yes. Standard blockchain technologies, particularly those relying on elliptic curve cryptography, ECC for digital signatures like Bitcoin and Ethereum, are indeed vulnerable to Shor's algorithm running on a future quantum computer. An attacker could potentially derive a user's private key from their public key, allowing them to steal funds or forge transactions.
So crypto wallets could be emptied.
Potentially, yes, if no action is taken. But thankfully, solutions are being actively developed here, too. Instead of requiring entirely new blockchain systems from scratch, many existing blockchain technologies can be modified or upgraded to enhance their security against quantum attacks. Blockchain's inherent decentralized nature already provides strong security foundations through distributed ledgers and cryptographic hashing, which is generally considered more quantum-resistant than public key crypto. By integrating quantum-resistant digital signature schemes like those standardized by NIST and potentially quantum-resistant hash functions, we can ensure the long-term integrity and security of digital transactions, smart contracts, and sensitive information stored on blockchains in the quantum era. This is crucial for protecting everything from cryptocurrencies and NFTs to decentralized finance, DeFi, supply chain tracking, and digital identity management. It's about quantum-proofing the foundations of Web3 before the threat fully materializes.
Okay, good to know that space is working on it too. Finally, it sounds like quantum machine learning, which we discussed earlier as part of QAI, isn't just a potential future capability. It's also emerging as a powerful tool within cybersecurity itself, right? How can QML actually help us defend against the very threats quantum computing helps create? It seems like we're coming full circle.
That's the wonderful paradox, isn't it? Yes, advanced QML algorithms are being actively researched and developed specifically to create smarter, faster, more agile cyber defenses. Examples include things like quantum support vector machines, QSVM, which might excel at classifying large-scale security datasets to find anomalies, Or quantum deep learning QDL techniques potentially better suited for analyzing high-dimensional data streams like network traffic or complex system logs to detect sophisticated intrusions. And even quantum genetic algorithms could be used for optimizing feature selection in threat detection models, identifying the most critical indicators of an attack.
So using quantum's power for pattern recognition and defense.
Exactly. Leveraging quantum principles to find those subtle attack signatures, predict malicious behavior based on faint signals, and adapt defensive postures to evolving threats with the speed and accuracy that might eventually surpass purely classical AI capabilities in certain security tasks.
And I understand these various QML approaches can be integrated together, perhaps even with classical AI, into something called ensemble models. How does that work?
Precisely. An ensemble model approach combines the strengths of multiple different machine learning models, potentially a mix of classical AI models and various QML models, creating a layered, more robust defense. By combining diverse perspectives and algorithms, these ensemble systems can often achieve better overall performance, resilience, and accuracy than any single model alone. In cybersecurity, this multi-model approach could significantly enhance our ability to identify complex, multi-stage cyber events, detect sophisticated, low and slow attacks in real time, optimize network routing for both security and efficiency simultaneously, and manage computing resources effectively to dynamically repel advanced threats. The result aims to be more robust, adaptive, real-time cybersecurity defenses that can proactively counter sophisticated, evolving threats in the quantum age, essentially fighting quantum-accelerated threats with quantum-enhanced defenses. Hashtag outro.
What's truly fascinating here as we wrap up is just the sheer compounding pace of technological advancement today. It feels unlike anything we've witnessed before in human history. We're not just dealing with one single emerging technology disrupting things. We have multiple profoundly impactful shifts happening simultaneously. AI, quantum, biotech, advanced materials. And quantum AI, the specific convergence we've explored today, seems to be compounding its impact on society, on finance, on our security, and frankly, on just about every single facet of our increasingly digital existence. It's creating both these incredible, almost utopian opportunities and some really significant, quite sobering challenges.
That's absolutely right. And it's crucial to remember, quantum computing is no longer purely theoretical, confined to university whiteboards. It's making significant demonstrable progress in labs and research institutions worldwide. You see breakthroughs announced almost weekly, it feels like sometimes. Governments globally are recognizing its strategic importance and are investing heavily billions of dollars in research and development. And that quantum advantage we talked about, that tipping point where a quantum computer can genuinely solve a commercially or scientifically relevant problem faster than any classical supercomputer. Well, some credible estimates put that possibility just 5 to 6 years away for specific applications, maybe sooner for others.
5 to 6 years. That's really not far off at all.
It's not. And what's more, cloud access to actual quantum computers is already a reality today. Major players like IBM Quantum, Google Quantum AI, IonQ, Rigetti, Xanadu, Amazon Bracket, they offer cloud platforms where if you're proficient in quantum programming languages like Qiskit or Cirq, you can right now remotely access and experiment with real quantum machines. The future is quite literally at your fingertips, online, waiting to be explored and built.
Which brings us directly to our call to action for you, our listener. This whole discussion isn't about some distant, abstract problem for future generations to worry about. The transition to a quantum-safe cybersecurity landscape in particular is not optional. It's an imperative that demands attention now. Procrastination is really not a viable strategy here. You and the organizations you work for or lead must start recognizing these looming cryptographic threats and begin proactively engaging with, planning for, and eventually adopting quantum-resistant solutions. This is essential to safeguard sensitive information, protect critical infrastructure, and maintain robust security in the coming quantum era. Waiting for the quantum boom to be fully upon us, allowing those powerful code-breaking algorithms to mature without adequate protection in place, is simply not an option if we want to avoid potential chaos.
Well said. So, as you go about your day, maybe mull over this provocative thought. In a world where quantum machines can eventually outsmart our current encryption in mere moments, and where AI can learn, adapt, and potentially manipulate at speeds we can barely comprehend, how will we collectively and individually redefine the very concept of trust in our digital interactions? What will it mean to trust a system, an algorithm, or even information itself in that future? And perhaps more personally, What responsibility do we each have, not just to passively keep up with these monumental technological changes, but to actively participate in shaping this rapidly evolving quantum AI landscape? How can we ensure it develops into one that is more secure, more equitable, more transparent, and ultimately more beneficial for everyone? It's a future we're all building, consciously or unconsciously, one qubit and one algorithm at a time.